Okay, students. So yesterday we had seen about the different applications of neural network. Now we saw clustering, we saw classification. Now today we shall have a look at what is vector quantization. So before what we see is vector quantization, we shall have a look at what is quantization process. So you all must have studied in communication engineering what is quantization. So basically, it is a process of constraining an input from a continuous or large set of values to discrete set. So a simple example which I can take here is that if at all the value lies between 0 and 1, okay, it can be anything, it can be 0.001, it can be zero point 0.6, it can be zero point 0.7, it can be anything. So what is done is that in that case the value will be assigned to zero point 0.5. So whenever it is lying between 0 and 1, it is assigned to zero point 0.5. So here between 0 and 1, I have infinite set of values. In this infinite set of values, I am assigning to a fixed value that is zero point 0.5. Similarly, from 1 to 2, if at all I have any number, then I will be assigning it to 1.5. So from 2 to 3 and so on. Now, if at all we take a value of say 93.8, so 93.8 will be mapped in this case to 93.5, because if at all you have seen any value between 2 and 3 will be given the average, that is 2.5. Similarly 3 and 4, any value will be given 3.5. So similarly any value between 93 and 94 will be assigned the value 93.5. So this is simple example of quantization, just for you all to know what is quantization. Another example I have taken, that is if at all the value is in between minus zero point 0.5 and zero point 0.5, I am giving it a value 0. Or if at all it is from zero point 0.5 to 1.5, then I'm assigning it a value as 1, and so on and so forth. So if at all using this example, if at all we try to find the value of 93.8, it will be quantized to 94. So in this case, you can say that an example is given here, that is a set of values such as real numbers is going to become a discrete set such as integers. Okay, this is exactly what is happening here in the second example. So 93.8 becomes 94, 92.7 will become 93, 5.1 will become 5. So you will have all integers which will be present. So this is a form of quantization. So if at all you see what is quantization, okay, now this is scalar quantization, because you are taking a scalar, just one value, and you are converting it into a quantized value. Okay, so basically it helps because the output set of values is limited. Okay, so from real numbers we can convert to integers, or basically whatever is the output will be limited data. So basically what we get is data compression. So we are able to achieve data compression because from a large data we can get a limited data, and that is what is the advantage of quantization. Now so far we have seen scalar quantization. Now, scalars. Now, we in neural networks, we will not be working with scalars mostly, but we will be working with vectors. So, in a pattern space, whenever we consider it, we consider mostly two-dimensional pattern space. Okay, wherein the vectors are having x1 and x2. Two variables will be there. Similarly, I can have a vector space which is three-dimensional, that is x1, x2, and x3, or I can have four dimension or any other dimension. So whenever I mean to say dimension, it will be talking about the features in the pattern space. So if at all you have a 2D pattern space, it will be 2D feature space, meaning two features you are going to have. So moving on to vector quantization. So basically, what is vector quantization? So it works by dividing a large set of points. Now, in previously also we had a large set of points, but they were scalars. So I had divided the points, the scalar points from 0 to 1. They were given one particular value, which was the average of it. Average meaning average of 0 and 1 divided by 2. If at all you do, you'll get zero point 0.5. 1 and 2 divided by 2 will get 1.5. So like this. So similarly here, what we are going to do is that we are going to take a set of vectors. Now please note, vector is not here, it is just a scalar previously. But vector will be, say, supposing there is a vector 1.5 comma 2, that is a vector, or it's a two-dimensional vector. So we usually work in neural networks with vectors. So what will be done here is that the vectors in the pattern space will be grouped, and they will be approximately grouped in into groups having the same number of points closest to them. So it may not always be the case, but each group will be represented by its centroid point. So say for example, these whatever I have highlighted here are all vectors. Okay, all vectors in the pattern space, in a 2D pattern space. So these are all vectors. If at all you take points and if at all you plot, you will get them. Now, what is done is that these patterns in the pattern space are classified into three regions, if at all you see. So large pattern space is divided into three regions, and these three regions, or all the values which come in this particular region 1, are assigned this particular centroid value. So they are finding the centroid of all the points, and or any of these patterns will be represented by the centroid point. Okay. So the neural network can be used for compressing voluminous input data into small number of weight vectors. Now, if at all you see these points, there are so many points in one cluster, the second one, and in the third one, three regions which I have shown here, there are so many points. But finally, this region will be represented only by 1 point. This one with 1 point, this region will be represented by 1 point. So basically, each of them will be represented by their centroid points. So if at all I am dividing into three regions, I will be having three centroid pattern vectors. Okay, so that is the reason we are able to compress the data from so many pattern vectors into just three vectors. Now, each input sample is associated with the nearest weight vector. Okay, say for example, if at all I take this particular point here, sorry, supposing I take this particular point here. So I have to calculate the distance between this centroid from here to here and from here to here, and whichever is the least distance, it will assign to that particular centroid. So that is the meaning of this statement. Now, vector quantization, I can say that it is a process of dividing up the space into several connected regions, and these regions are called as Voronoi regions. So you can see here, this is the pattern space, which is divided into three regions here. Okay, this is one region, this is the other region, this is the third region, and all are connected regions. Now, each of these regions are called as Voronoi regions. Now, you can see that vector quantization is somewhat similar to clustering. Okay, so in clustering also we are forming clusters, but this is different. Okay, so here the pattern space will be divided into connected regions which are called as Voronoi regions. Okay, it is similar to clustering, but it is different from that. Now, each region is represented by a single vector called as the codebook vector, and every point in the pattern space belong to any of these regions and is mapped to the corresponding codeword vector. So in these, supposing in these regions, in this previous case also, there was a code word vector. This was the centroid point. That is nothing but the code word vector. Okay, or sometimes if at all you do not want to use the centroid point, you can use some other code word vector as well. So now see this. This is a Voronoi diagram in 2D space, and there are five Voronoi regions. One, this is the first one. Sorry, this is the first one. Then the second one, then the third one, fourth one, and the fifth one. And each of these region is represented by a code word vector. So C1 is the code word vector of region 1, C2 is the code word vector of region 2, C3 is the code word vector of region 3, C4 is the code word vector of region 4, and so on and so forth. So each point in the input space belongs to one of these regions. Yes, because this is the pattern space, whatever is shown in this square, and any point which comes in this will be belonging to any one of the five regions, and it will be mapped to the corresponding nearest code word vector. So supposing there is a point here, here there is a point. So I have to find out the distances between the code word uh, vectors, between this point and all the other code word vectors, say from here to here, then from here to here, then from here to here, like this I have to find, and whichever is the shortest distance, there I will be assigning. So this point will be assigned to that particular code word vector, or the nearest code word vector will be assigned to that point. So the set of code word vectors is a compressed form of the set of input data. Now here the input data will be infinite, it will be quite large, but I will be having only five code word vectors. So it is a limited data. Okay, so many of the input vectors will be mapped to the same code word vector. So it will be a limited data. Now, figure represents, okay, this I have already told you. Now, how will you be finding these lines in the pattern space to separate into Voronoi regions is basically you would be drawing the uh, points, sorry, you would be drawing lines in between these points. So I have C1 and I have C2, then I have C1 and C3, then I have C3 and C4. So I'm going to draw these lines, and then what happens is that I will have to draw the perpendicular bisectors to these particular points. So from here to here, then from here to here. So like this, I'm going to draw these lines which are joining the centroids, and then the other dashed lines, whatever you can see, they are all perpendicular bisectors. So you can see here, this is the perpendicular bisector between this and this. Okay, so similarly, all the others will be the perpendicular bisectors, and by joining the perpendicular bisectors, you have got these regions. Okay, now we go to the actual part of today's class, that is linear vector quantization. So linear vector quantization is one of the techniques which is included in Unit 3. That is the reason first I have explained to you what is vector quantization, and now we will be moving to linear vector quantization, which is an application of winner-take-all networks in order to solve the problem of classification. So now we have seen previously unsupervised learning and clustering techniques. Okay, now whatever we have seen, that is simple competitive learning, is meant for clustering purpose. It is not a supervised learning technique, it is an unsupervised learning technique. So what happens is that The unsupervised learning techniques, that is your winner take all learning technique, is an unsupervised learning technique. Now they can sometimes be used to solve classification problems also. Please note, classification problems are supervised learning problems and clustering problems are unsupervised learning problems, as I have told you previously. But what I'm doing here is that I'm using winner take all networks, that is an unsupervised learning network, to solve classification problems. And to do this, we use a linear vector quantizer. Okay, so we will be using a learning vector quantizer. It is also called as linear vector quantizer. So an LVQ is nothing but it will be an application of winner take all networks for such tasks. So it is it will be illustrating how unsupervised learning can be used to perform supervised learning. So basically here, in the previous case, wherever we have solved a simple competitive learning, there is nothing told to us about the class membership. Okay, what we do is that we only take it into consideration. What do we take into consideration is we take which is the winner node, and whichever is the winner node, the weights of the winner nodes are updated. But now what happens is that in this case, uh, what happens is that we would be uh, y- y- also knowing the class membership of the pattern. So it is a supervised learning. It is, or whenever you are presenting the data, you will know which class it belongs to. So now each node in an LVQ is associated with an arbitrarily chosen class label. So in the output layer, what will happen is that there will be, supposing if at all there are three classes, then there will be three nodes. So the number of nodes is chosen for each class. It is roughly proportional to the number of training patterns that belongs to that class. Okay. So making the assumption that each cluster has roughly the same number of patterns. So that we are assuming. So we are going to assume that mostly, supposing there are six patterns, three belong to class one, three belong to class two. Now, what is the update rule in LVQ? The update rule in LVQ is different from that of the simple competitive learning networks. Now, in simple competitive learning, what we do is that we take the winner node and update the weights of the winner node. That is the update rule of simple competitive learning. Now, what is the rule of LVQ? Now, we are knowing that the pattern belongs to class I and the winner node J star belongs to class J star. So, for example, I am already supposing in the question we are presenting the pattern from class 1 and the node winner node is node 2. Now, what happens is that class 1 pattern is presented and winner node is from class 2. So basically, what I need to do is that the pattern and the winner node is not from the same class. So in that case, I have to move away from that, meaning the weight updates have to be negative. And if at all, I present a pattern from class 2 and the winner node is also from class 2, that is Ci is equal to Cj star, then I have to move the pattern towards the uh, pattern I. So the weights will be updated in the positive direction. Fine. So this is what is the learning rule here. So finally, the weights of the winner node are updated here always. Okay, in case of winner take all networks, we always update the weights of the winner node. But in this case, either there can be a positive weight update or a negative weight update. So when will be the weight update positive? If at all, the same class it belongs to. Say supposing class 1 pattern is presented and winner node 1 is producing the maximum output, then it is going to be a positive weight update. And if at all, say supposing pattern is from class 3 and winner node is 1, then I have to give negative weights for winner node 1. It is a negative weight update. Fine. So we will be going in details of that learning vector quantization. So there will be a problem which will be there.